Okay, let's solve one of your homework problems from the book. And we're just going to take a little bit of time here, so we'll take one of the ones that's a little more straightforward and work through it. So let's take a look. Problem number 26. A particle's position on the x-axis is given by the function x equals t squared minus t, 4t, I'm sorry, t squared minus 4t plus 2 meters, where t is in seconds. And then they ask us to do a variety of things. So let's just first get that part down, okay? Let's just write it down kind of up here in the corner. We know that this function of x is equal to t squared minus 4t plus 2 meters. All right? So we know that to start. And then they ask us a variety of things. They ask us first to make a position versus time graph for the interval between 0, when it's at rest, to 5 seconds. Between 0 less than or equal to 0, t is less than or equal to 5 seconds. And we want to go ahead and do that calculation and just figure that out. Then they ask us to determine the particle's velocity at time 1 second. How fast was that going at times 1 second? By drawing a tangent line to our graph and measuring its slope. Then we're asked to determine the particle's velocity by evaluating the derivative. So now we're going to take the graphical way to find that, because we have a varying velocity. It's not constant, and it's not uniform. So then we're going to do it by taking the derivative, and then they ask us some questions. Where are the turning points in that particle's motion, and what position? And we want to know, where is the particle when velocity is 4 meters per second? And then they ask us to draw a motion diagram. So first off, let's just get this diagram. Let's get this graph set up. So very first thing we want to do is let's get the graph set up. So let's go ahead and just set up a graph here real quickly. So all the best I can, drawing a straight line here. Let's just pretend we have graph paper. We'll set that as one of our axes. There's our other axes. And we're going to go ahead and just set this up. You know, I probably, given what I think that graph's going to look like, let's start about here. See how we do. And we'll set a couple things up here. This over here, this is going to be time in seconds. And this axis up here is going to be my x position, oh, excuse me, in meters. Now let's go ahead and we can just plot the points on there. So if we go through and just find the points and plot them on there. So I'm going to go ahead and do that calculation, get the points on there, and then we'll come back and we'll, do the curve. Let's go ahead and just set up a few things here. So we're going to say this is 0. So let's go up, I don't know, we'll go up 7, 8 meters. So this would be, roughly 1, 2, 3, 4, 5, 6, 7, 8 meters. So we'll just put 1, 2, 3, 4, 5, 6, 7, 8 meters. We'll go out this way. We may stretch the graph out a little bit, but we'll just say this is 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. And we'll just see what it looks like by doing that. So we've set those coordinates on our to set the scale on our axes, and we'll just see what it looks like. So now, all I've done is I've kind of figured it out, plotted the points. They ask us to find a point at half-second intervals, and then draw that. So we can take and basically draw this curve to go up through there. So that kind of gives us an idea what that looks like on that, and that's what that function looks like there. And then they ask us, once we've got that, they want us to determine the particle's velocity at 1 second by drawing the tangent line on your graph and measuring its slope by drawing the tangent line. So now we're going to use a graphical method to do that. So here, if we're just drawing this graph, if we took a ruler now, if we were just to take a ruler and come over to this and find 1 second, and again, this is, you know, you do the best job you possibly can. It's not perfect here, but let's just draw a tangent line there. So there we go, that's pretty close. A tangent line there, and that slope is, okay, that is our velocity for this particular particle, okay? And then we have to go ahead, draw the tangent line, and measuring its slope. So we're going to, you know, come up with a couple points on this line. So, you know, choose the points graphically for that line. And this is a little more difficult because you're going to have to find something and figure out what it is. And remember that we still have that velocity up here is equal to our change in position over a change in time. So we've got to come up with 2 points. So I'm going to just see if I can pick a different color here. Let's pick green. I'm going to use this point right here, okay, 2 seconds, and I'll use, let's just say, where it crossed, or we can just say here, makes it a little easy, on the x-axis. We'll use those 2 points, okay? So we can use those 2 points and see what we get. So on the x-axis, what we get is about a minus, you know, I didn't draw that, you know, 1 point something, 1.8, or so, not 1.8, 2.8, something like that. So we're going to have, if you evaluate that, okay, x, where you final minus initial, we're going to have our 0 minus 2.8 about. Time-wise, where were we at? Well, we ended at 2 seconds, we started at 0.5, so we got about 2 minus 0.5. Started at 0.5, ended at 2, about there. And, you know, go ahead and evaluate that, and we can determine, you know, graphically about what is our velocity. Doing this, I get at that point in time about a minus 1.86 meters per second, or 1.9 meters per second, roughly. Okay? And that's doing it graphically, by finding that tangent line, you know, using a ruler, do it graphically. The next thing they're asking us to do, so that's part A. The next thing they asked us to do, part B, was to find out, in this problem, find what was that velocity at 1 second. But now, instead of using the graphical method, which is close, they're asking us to find the derivative. So now we're going to use that calculus to find the derivative of this function. Okay, now we talked about this. If we looked at this line over here, and we picked a point here and here, but if we were to take these points and move them closer together, we move that time frame as it approaches 0, we're going to say, as we narrow that to 0, we're going to hone in at that instant in time. And that was where we talked about in calculus this idea of the limit, finding that little piece of time, and it's so narrow that the slope at that piece of time, it's essentially a straight line, and we found that slope very accurately. And that is really, as we take the limit, we can simplify that a little bit, and mathematically, that we can say is the derivative, which equals the velocity in the x direction. And we're just going to look, if you go to the back of your book, there's a lot of theory we said about that talks about the limit and everything. The derivative is the slope, the derivative of that function is the slope of the line tangent at that point that we're evaluating. We can go to the back of the book and we can look up some of the various derivatives that we'll use, some simple ones, to make it a little easier. So this particular one we can look at and say is of this form. And I'm just going to put it down here real quickly. Of the form on your book, it's actually on page, or it's appendix A3. If you go to the back of your book and we look at this ax to the n, some constant times x to the n, if we take the derivative, it looks like this. N times a, x to the n minus 1, okay? So let's come up here and see what does that look like, because we have our function here, t squared minus 4t plus 2, okay? So we're going to take the derivative of that, and that equals, we take the derivative of that, that equals the velocity of this particular unit. So let's go ahead and do that. Let's take the derivative. Well, that then is 2t, 2 minus 1, and so it's just 2t, minus, well, if we do this here, 1 times 4 is 4, but 1 minus 1 is 0, so we end up with just 4. And when you take that function, the derivative of a constant, the constant goes away. So this ends up being 2t minus 4 is what our velocity is equal to. Now if we evaluate that at zeros, at 1 second, so we put in 1 second, we end up with 2 minus 4, and so when we do all that, we get our velocity as being minus 2 meters per second. And we can see it's pretty close. I was eyeball it, and I came, fairly close, but it wasn't perfect, and it takes a whole lot less time as we, start doing these and evaluating this. And taking the derivative, when we have something, we're looking for an instant in time, which this is asking us. Now we go up and look at the graph, and it's asked us, determine the particles, or determine any turning points in the particle's motion. That point in time, for an absolute instant in time, okay, and an instant in time where it's changing. And we find that, those turning points to be, and it asks us, were the turning points of particle motion? If so, at what position or positions? So where are there turning points? Yes, we have a turning point at 2 seconds, and at an x equals minus 2 meters. So if we come over here at 2 seconds is where it's changing, and that happens to be minus 2 because this is minus 1 minus 2. So x equals minus 2, and 2 seconds is that turning point. Where is the particle when you're at 4 meters per second? Well, we know this. Let's see if I can shrink this up. If I'm lucky, I can shrink just this piece up real quickly. No, I gave me the whole thing. Well, we'll fit it in. We'll just fit it in right down here. So what about when x, or when the velocity is 4 meters per second, where is the particle? Well, we know this. We know velocity, we know the velocity in the x position. So this would be part E, I guess that is. We know the velocity in the x position is equal to what? Well, the velocity in the x position is equal to 2t minus 4. I know the velocity, so let's solve this for t. When we solve this for t, we're going to get t equals v sub x plus 4 all divided by 2. So at 4 seconds, evaluating this at 4 seconds, we'd have 4 plus 4, 8 divided by 2. Time is equal then to 4 seconds, if we put that in, okay? So we get 4 seconds. Now, at time equals 4 seconds, we can take that then back into the initial position function up here, plug it back into there, and I'll let you plug it back into there. Now we get our initials. We put 4 back into there, 4 seconds back into there. We're going to get 4 squared, so we get 16 minus what? 16 plus 2. We get x is equal to 2 meters. And if we go back and look at the graph, sure enough, that's what it is. So again, a simple example of a problem where you have a function, the velocity is changing, and it's not changing at we're wanting an instant in time, again, and we can use both an example of a graphical method, and an example of using calculus, using the derivative to be able to find that.